Welcome everybody to another session from Nairo Research. I'm Srijit here, and in this session we are going to continue by briefing the applications of AMS band with NEGF function. So in this video, I'm going to brief you about how spin transport in chromium wire can be investigated using NEGF formalism. So what are the significance of chromium, especially when it comes to spintronics? Obviously, anti-ferromagnetism and spin density waves. Chromium is one of the material due to its antiferromagnetism characterized by the spin density wave order. This arises from the Fermi surface nesting where electron and hole pockets align, leading to the modulated magnetic structure. And the unique spin properties, unlike other ferromagnets where spins are uniformly aligned, antiferromagnets have alternating spin alignments which can lead to a different spin transport phenomenon, making chromium an interesting candidate for novel spintronic devices. And speaking about NEGF band formalism for the spin transport, obviously, like I explained in the previous videos, NEGF is a powerful quantum transport formalism that allows for the simulation of electrons and spin transport in nanoscale devices under non-equilibrium conditions. It particularly well suited for systems where scattering and quantum coherence play a key significant role. So NEGF calculates the Green's function, which contains information about the electronic states and their propagation through the device. From this, quantities like transmission functions and currents can be derived. And also how band can be used. Band, of course, it's a density functional theory based code for materials or periodic systems, can be used to calculate the electronic structure. When coupled with NEGF, it provides the necessary Hamiltonian and overlap matrices for the transport calculations. And speaking about unrestricted DFT to account for spin polarization and magnetic ordering, the unrestricted DFT calculations are crucial, which allows for different spatial distributions of spin up and spin down electrons. And speaking about spin orbit coupling, for a complete picture of spin transport, especially in materials with heavier elements like transition metals and inner transition metals, including spin orbit coupling in DFT calculations is very important. So spin orbit coupling can couple the electron spin to the orbital motion, influencing spin scattering and spin current generation. So speaking about the typical workflow for NEGF band simulation for spin transport in a chromium wire, let me show you that how we can generate this picture. So let me open up a new input, and within few seconds it will open up a new input. So I have already created one calculation. Let me show you that how we can form or create a workflow. Just need to select band, and then we need to select the task NEGF. So it's already done, and then we need to load the lead. So I have already downloaded the Chromium lead here, and I'm just opening it. You can see the right and left electrodes, and then I'm just filling the central region. So it should be a 9-layer one-dimensional chromium bias molecules, and then I have set this calculation workflow, and before that we need to set this unrestricted. So why? So speaking about the structure setup, I have designed the chromium wire as the central scatter region. This includes to be a one-dimensional chain of chromium atoms or a segment of bulk chromium structure. It will define semi-infinite chromium leads attached to both ends of the wire, ensuring proper periodicity. It will consider the crystallographic orientation of the chromium wire as a magnetic properties can be isotropic. And to perform a spin polarized DFT calculation for the chromium leads and the central region using band module, we have to enable unrestricted option to account for spin polarization. So that's why I have opted out this unrestricted option. So to determine the ground state magnetic configuration and the corresponding spin dependent band structure, if relevant, which includes spin orbit coupling,